Hi viewers. In the previous session we discussed regarding some basic elements or basic things whatever we have to learn in the chapter of electric current, that is about the division of electricity, static and current electricity. And in case of current electricity, we have discussed regarding electric current, electric potential difference, electric field and electromotive force. And even electric current, the units are amperes, and electric potential difference and even electromotive force, the units for all these things are volts, as we discussed previously. Ampere, already I defined ampere. Ampere is nothing but if I equals to Q by T, if 1 coulomb of charge is brought in 1 second, then we say the electric current is 1 ampere. Similarly, electric potential difference is nothing but the difference in the two potentials. That means in an electric field, inside the electric field, the difference between the two electric potentials is nothing but electric potential difference. Generally, in our common language, we say it as voltage. Okay, now let us move on to the next session, that is regarding Ohm's law, the concept of resistance, and what are the factors that affect resistance and specific resistance or resistivity. Then Violet, this is SANTHOSH Kumar and welcome to my channel Sims Academy. Today we are going to learn about Ohm's law, its limitations, next resistance, factors affecting resistance, the concept of resistivity. Okay guys, and in the last video I asked you a question that is electric current a scalar quantity or a vector quantity? Okay, electric current, generally we define a scalar quantity is a physical quantity which possesses only magnitude, that means numerical value and unit. Yes, but it doesn't possess any direction. But vector quantity possesses both magnitude and direction. Here let us consider a small circuit. Here this is a cell, current is moving. Yes, current is following a particular direction. We can say in this way, in this direction it is moving, here in this direction, here in this direction. But why don't we say, is it a scalar? Electric current is considered as a scalar quantity, but it is not a vector quantity. Why that one? Because even though it contains both magnitude and direction, it does not follow the other two laws. What are those two laws? The triangular law of vectors and parallelogram law of vectors. If we consider here, it is coming to the same position, in the sense the electric current should be zero in the circuit, but it is not zero, some current is present. Hence it does not, even though it possesses both magnitude, electric current, suppose 5 amperes of electric current is flowing in the circuit. Yes, and it possesses a direction also, from here to there it is moving. Okay, both magnitude and direction, but it does not follow the two laws of vectors. Number 1, triangular law of vectors, and number 2, parallelogram law of vectors. Hence, electric current is considered to be a scalar quantity. Okay, and next, electric current. How do we measure electric current? Electric current is measured by an instrument called as ammeter, and it is denoted with this symbol. electric current and electric potential difference, which generally we say it as PD, or voltage. It is denoted by an instrument called as voltmeter. Don't get confused between voltmeter and voltameter. Voltmeter is a device which measures voltage or electric potential difference, and voltameter is a vessel in which we carry out the process of electrolysis. The vessel in which we carry out the process of electrolysis, we say it as voltameter, and the instrument which measures electric potential difference or voltage in the given circuit is called as a voltmeter. Volta, volt, a small difference we have to observe. And one more important thing, ammeter should be always connected in series in the given circuit, and voltmeter should be connected always in parallel to the given electric consumer or electrical resistance. That's what we are going on now. Yes, ammeter should be connected in series in the given electrical circuit, and similarly voltmeter should be connected in parallel to the given electric consumer or resistor. Got it? Why? Because in series combination, in series current remains constant. I is constant, and in parallel combination V is constant. Hence we always connect this ammeter in series in a circuit and the voltmeter in parallel to the given electric consumer. Okay, now let us build a small electric circuit. Here we shall mention what is that? Ammeter, always connected in series. It measures current. Voltmeter, it should be connected in parallel and it measures voltage. This is a cell. If I take a group of cells, then we say it as a battery. Already we discussed previously how the energy is stored in a cell or a battery. The energy that is stored in a cell or a battery is in the form of chemical energy. Chemical energy gets discharged whenever it is used up. Now let us connect a cell an ammeter. Ammeter measures electric current and it should be connected in series in the given circuit. Switch key, let us take a conductor, a manganese or nichrome, or generally an iron spoke it is given. Let us take the iron spoke in between the points P and Q, we shall suppose, and I am connecting a voltmeter across this iron spoke PQ. Why did I connect that voltmeter in parallel over here? Why? Because voltage remains constant in the parallel combination and voltmeter should be connected in parallel in the given electric circuit to the electric consumer. Here the electric consumer is iron spoke. Now let us suppose this is a 2 volt cell. Now the key is closed such that the current flows through the circuit. Here let us suppose this is voltage, this is electric current, and let us take the ratio of V to I over here. Yes, initially we have connected to a 2-volt cell. Let us assume the current that is read in the ammeter be 1 ampere. Now I would like to increase the voltage. How should I increase the voltage? If I add another cell, that's enough for us. Yes, another 2-volt cell. This constitutes a battery. Here we have a battery of 2 plus 2, 4 volts. Let us say the ammeter reads 2 amperes, just a hypothetical observation, not exact one. For our understanding purpose, I am writing over here, and even I have done this experiment of Ohm's law, verification of Ohm's law. If you type in my videos, the very first video was that one. Verification of Ohm's law was being given. We can see the connecting, how I connected the voltmeter, the ammeter, and how the readings are shown. Both voltmeter and ammeter are also shown in that activity. You can go through that. But these are the just imaginary one for our understanding purpose. I am taking another cell of 2 volts. Now we get total of a battery consists here. A battery constituting 6 volts voltage. Let us say the ammeter reads 3 amperes. Now let us take the ratio of V to I. 2 by 1 it is 2, 4 by 2 it is 2, 6 by 3, 3. 6 by 3 is also. Now finally I observed here in this particular activity, I did not change the temperature. Temperature remained constant because I haven't done with 2 volt cell in this room, and I did not go somewhere else for after connecting 2 volts. In the same room I have done. That means there is no change of temperature, and as I increase the voltage in the circuit, the electric current seems to increase. That means the ratio of V to I is going to be constant, and this is called as Ohm's law. V by I equals to constant, and we say it as Ohm's law. Here Ohm's law is also verified. How can we define this Ohm's law? The potential difference or the voltage across the two ends of a conductor is directly proportional to the electric current, provided the temperature remains constant. That is very important, right? We should mention. Or easily in mathematical form we can mention it as the ratio of V to I in a given circuit is always constant for a constant temperature, provided there is a constant temperature. This is Ohm's law. Now from that I can write V is proportional to I. Now I'll draw the graph. If I draw the graph by taking V voltage on x-axis and the current on y-axis, I'll get a straight line that passes through the origin. Now let us change this activity. Instead of iron spoke, let us take a semiconductor like germanium or silicon, or instead of that let us take a LED, light emitting diode. A diode is connected over here, LED, okay, because I cannot draw LED properly. I cannot draw well because I am not a good artist, okay. Here instead of that iron spoke I have taken LED, but from the observations we came to understand that the ratio of V to I for this case, in case of LED, was not found to be constant. If I draw the graph from V to I, we don't get a straight line, we get a parabola. That means V to I ratio in case of LED, this is iron spoke I have taken. Here V to I ratio, V by I equals to constant, but here V by I is not equals to constant. Hence I got a parabola over here. That means these kind of semiconductors like germanium, silicon and LED, of course it is made up of the semiconductor devices, and these, they are not obeying Ohm's law. Hence we call them as, these are conductors. Of course they conduct electricity. These are conductors, but they do not obey Ohm's law. Hence we say them as non-ohmic conductors. Non-ohmic conductors. Here this iron spoke and all metals generally they obey Ohm's law. That means the ratio of V to I is found to be constant every time. Hence these are called as they are obeying this Ohm's law, that is V by I equals to constant. Hence we say them as ohmic conductors. Now finally I have classified the conductors into two types based on Ohm's law. Number one, ohmic conductor, and number two, non-ohmic conductor. What are ohmic conductors? Generally all metals are very good conductors and they are obeying Ohm's law, hence they are considered to be the ohmic conductors. How do we get the graph in case of the ohmic conductors? The graph is a straight line which passes through the origin. What are non-ohmic conductors? The second case, the conductors which do not obey Ohm's law are called as non-ohmic conductors. How will be the graph of the non-ohmic conductors? The graph is a parabola. Non-ohmic conductors are also conductors. They do conduct electricity, but they do not obey Ohm's law. What are the examples for that? All semiconductor devices. That means we came to understand Ohm's law. At a constant temperature, the ratio of V to I must be constant. V by I equals to constant. Now coming to the point. What is that constant? That constant. What is that constant? That constant is called as electrical resistance. What do we say that one as? That constant is called as electrical resistance. That means for in case of ohmic conductors we have R. R is nothing but electrical resistance. The name itself indicates resisting. Resistance, resisting means to oppose. To oppose. To oppose what? The free flow of electrons in the conductor. If I oppose the free flow of electrons in the conductor, what happens? The conductor gets heated. That's what the main principle of working of an electric bulb. The filament in the electric bulb shows a very high resistance, hence it gets heated up immediately when it is switched on, and because of heat always produces light. Hence electric bulb glows immediately. Even we can see lighters in the pawn shops. They switch on that when the small filament is kept, it gets heated up, they light, they go. Okay? That means V by I equals to constant according to Ohm's law. That constant is called as electrical resistance. Electrical resistance in the sense to oppose the free flow of electrons. Free flow. No, there is no free flow. If we go to the temple, what do they do? Suppose I went to Sai Baba temple. What they say? Sai Ram, go on, Sai Ram, go on. But here, in case of electrical resistance, these who are the mediators, they stop. they oppose the free flow of electrons. Don't go away, don't go away. That means there is a opposition that is exhibited on the free flow of electrons, and that electrical property of the conductor, we say it as electrical resistance. From Ohm's law we got V by I equals to R. R is called as electrical resistance, the property of a conductor by virtue of which opposition is offered to the free flow of electrons in the conductor. Got it? Oh, very lengthy. The property of a conductor in which opposition is offered to the free flow of electrons. In a simple manner we can write. No problem for that. Now we came to understand about the electric resistance. Okay. What are the units for this electric resistance? V by I. V means volts. I means current in the sense current. Units for current are amperes. Or 1 volt per 1 ampere, we say it as 1 ohm, given on the name of Simon Ohm's law. Okay, and the symbol for ohm is this one. Okay, 1 ohm equals to 1 volt by 1 ampere. Now, how do I define ohm? Electric resistance is said to be 1 ohm if 1 volt of, what is this? If 1 volt of potential difference causes a current of 1 ampere in the circuit. Understood? 1 volt per 1 ampere in the sense if 1 volt of voltage, that means the potential difference, causes how much amount of current? 1 ampere of current in the circuit, then we say the electric potential as 1 ohm. 1 ohm. 1 ohm equals to 1 volt by 1 ampere. I hope you understood well. Okay. Now, let us move on to the limitations of Ohm's law over here. Already we discussed the limitations. That means based on the Ohm's law we have classified the conductors into two types. Ohmic conductors, non-ohmic conductors. Ohm's law is applicable only for ohmic conductors. Ohm's law is not applicable for non-ohmic conductors. Ohm's law is applicable only for metals. Ohm's law is not applicable for non-metals. There are some, only one non-metal which conducts electricity, right? But there are some, what we can say, semiconductors. Yes, semiconductor devices, they do not obey Ohm's law. Even Ohm's law is not applicable when we change the temperature. The entire activity must be done at a constant temperature. Then only, even in case of ohmic conductors, if the temperature varies, even V by A ratio is not found to be the constant one. Hence, these are the limitations of Ohm's law, and we got to know about the electrical resistance, the opposition that is offered to the free flow of electrons in the circuit, and R equals to V by I. V is voltage, I means current. If 1 volt of voltage causes 1 ampere of current in the circuit, we say it as 1 ohm, and the symbol for ohm is this one. 1 ohm equals to 1 volt by 1 ampere. In the exam, we may be asked the question to draw the graph of ohmic conductors, to draw the graph of non-ohmic conductors. We may be given the graph and we may be asked, what does that graph represent? It may be of ohmic conductors or non-ohmic conductors. That depends upon the given graph, of course. Now, let us discuss. We cannot do all the activities, but let me just mention you that what are the factors that affect the electrical resistance. Already I told you whenever opposition is offered to the free flow of electrons, what happens? The conductor gets heated up. The conductor gets heated up. Whenever it gets heated up, is there any change in the temperature? Yes, of course, there is a change in temperature. Is there the increase in temperature or decrease in temperature? It gets heated up. That means more the resistance, more it gets heated up, there will be more increase in temperature. That means the very first factors affecting resistance. Number one, temperature. That means as R increases, temperature also increases. Okay, and in case of semiconductors like germanium, as temperature increases, the resistance decreases. This is very important thing we need to keep in our mind. As temperature of the semiconductor increases, like semiconductor, like the best example is germanium. Okay, if the temperature of the germanium increases, its resistance decreases because it is a semiconductor. Hence, we use those semiconductors for making LEDs, ICs, integrated circuits, etc. And the second one is the resistance of a conductor depends upon the material of the conductor. Material of the conductor. Nature of material of the conductor. That means as we know, the immune system is different for different people. Okay, I along with my brother, suppose we have gone to somewhere. Okay, I felt sick. After coming back, my brother may not, because I do have very pure immune system. Let us suppose. That means the immunity in the sense, in our physics language we say it as the resistance power differs from person to person. Yes, in the similar fashion, the resistance of a conductor depends upon the nature of material of the conductor. At the given temperature, at a room temperature, if we consider at 25 degrees Celsius, copper may show one value of resistance, iron may show one value of resistance, zinc, lead, silver, gold, all these metals, different metals will show different values of resistances. And I forgot to tell you, the substance which possesses the property of resistance is called as resistor. Yes, the substance which possesses the property of resistance is called as resistors. Yes, this is not in case of each and everything, because someone who draws cannot be called as something else, right? He is called as an artist. That should be kept in our mind. Now we have seen two factors that affect the resistance. Number one is temperature, and number two is nature of material of the conductor. And number three, resistance depends upon the length of the conductor. Resistance always depends upon the length of the conductor. And what happens if the length of the conductor is increased, the resistance is also found to be increased. If I increase the length of the conductor, the resistance of that conductor is also increased. Experimentally we can prove that. Next, and the last factor on which the resistance depends is area of cross-section of the conductor. Area of cross-section of the conductor. If area is increased, the resistance is decreased. Area, if it is increased, the resistance decreases. Yes, how could we increase the area? Suppose I have a small 1 centimeter conductor. Now another 1 centimeter conductor, both are, yes, what do we say? Both are connected together and rolled up. Then we can increase the area of cross section of those two wires. Yes, area of cross section is increased. We found it that if area of cross section increases, the resistance of the conductor decreases. If the length of the conductor increases, its resistance also increases. That means for a given temperature, the resistance is directly proportional to the length. The resistance is proportional to 1 by A. That means the resistance is inversely proportional to the area of cross section of the conductor. Hence, by combining those two, I can write it as R proportional to L by A, or R equals to some constant into L by A. Now what is that constant called as? That constant is called as specific resistance or resistivity. Specific resistance or resistivity, we use the symbol rho, 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 for the specific resistance or resistivity. That means if I rearrange, I get K equals to R into A by L. Yes, K equals to R into A by L. What is K? Rho. Rho equals to R into A by L. This is the formula for specific resistance or resistivity. And with what we denote that specific resistance or resistivity? Rho equals to R into A by L. Rho equals to R into A by L. And rho is called as specific resistance or resistivity. Now, what are the units for that? R ohms, area meter square, length meter. If I cancel, we get the units as ohmmeter, ohmmeter, or in symbols ohmmeter. These are the units for specific resistance or resistivity. Here now I consider area as 1 meter square, length as 1 meter. You see in this formula, rho equals to, I'll write here, rho equals to R into A by L. A I have taken 1, L as 1. Then what do I get? I get rho equals to R. If I take area as 1 meter square and length as 1 meter, then I get rho value, specific resistance value, as R. When do I get rho equals to R? If area of cross section is 1 meter square and length is 1 meter. I repeat again, if length is 1 unit, if area of cross section is 1 unit, then specific resistance becomes the resistance of the given conductor. Now can we define the specific resistance? Yes, of course. The specific resistance of a conductor is equal to the resistance, is equal to its resistance for 1 unit length and 1 unit of area of cross section. If the length of the conductor is 1 unit and area of cross section is 1 unit, then the specific resistance or resistivity is R, its own resistance. Hence we define it as the resistance of a conductor of unit length and unit area of cross section. And what are the units for specific resistance? Ohm meters. And what are the units for resistance? Ohms. Ohms are V by I, volts per amperes. Yes? Okay. Now we came to understand about resistivity, Ohm's law, limitations of Ohm's law, resistance, factors affecting resistance, and what is the instrument that measures electric current, ammeter, and how should be connected in the circuit. Ammeter should be connected always in series in the circuit. How should a voltmeter should be connected in a circuit? It should be connected in parallel to the given electric consumer. Okay, after this, the next session we are going to learn about resistors in series and parallel, and maybe some numericals based on that, if possible. And let us write all the formulae whatever we have got once, then we don't forget. Till now, the first one is electric current I equals to Q by T, units Coulomb per second or amperes, and electric potential difference W by Q, joule per coulomb or volts. And next we have got Ohm's law, V equals to IR, V by I equals to R, I equals to V by R. Anything? These are the different mathematical representations of Ohm's law. For better understanding, we have a triangle, we call it as a magic triangle. This is VIR. Whatever we would like to have, if we close that, we get the formula. If I want to get the formula for I equals to V by R. If I want to get the formula for R equals to V by I. If I want to get the formula for V equals to I into R. We say it as magic triangle. And after that, the factors that affect electric resistance, the first thing is temperature. As temperature increases, the resistance also increases. Next, nature of the material of the conductor, and length of the conductor. As length increases, the resistance also increases, and area increases, area of cross section of the conductor increases, the resistance decreases. And we have got about the specific resistance and resistivity of a conductor, and its units are we got rho equals to R into A by L, ohm meter. And how can we define that one? It is equal to the resistance of a conductor of unit length and unit area of cross section. Resistivity is also the property of the conductor. It depends upon the nature of material of the conductor. Every metal, every conductor has got its specific resistance. Hence we say it has specific resistance, hence resistivity. And what is the resistivity or resistance? In the sense to oppose the flow of electrons. If I allow the flow of electrons, if I oppose, we are saying it as resistance. If I allow, conductance. If I oppose, resistivity. If I allow, we say it as conductivity, even here. And the units for conductivity are, this is the magical thing, reciprocal, right? Reciprocal means 1 by ohm meter. Sarcastically, how they have given, you see, if I reverse that ohm, I get mho. Mho per meter are the unit for conductivity. Okay guys, so these are the formulae we have come across in the chapter of electric current till now, and in the next session we are going to have regarding the resistors and what happens when the resistors are connected in series and when they are connected in parallel. Until then, I am very thankful to you for watching the video. Okay, stay home, stay safe, and this is Santhosh Kumar from Sims Academy signing off. Bye.